All right, so in this video, we are going to derive the D2d character table. And so usually for these point groups, it's nice to have an example molecule that we can look at to derive all of the symmetry operations. And also we can use the name of the point group to help us out. So in this point group, we know that we have the number 2, so we're going to have a C2 operation. And that's going to be the principal rotation axis or along the principal rotation axis, right? And there's a caveat on this specific case, something a little bit out of the ordinary for this point group that we'll discuss. We have the small d there. That means we're definitely going to have sigma d's, right? Dihedral mirror planes. And then we have the capital D. And the D groups, the capital D, means that we always have n perpendicular C2s. And so perpendicular to the principal rotation axis, which is also C2. So we have, since our n is 2 here, we're going to have 2 perpendicular C2s, which we call C2 primes. So those are things to look at when we're going over this example molecule, which is allene. It's 3 carbons with 2 double bonds. And of course, we can always have the identity element, right? Which is just mathematically like 1. It's just doing the molecule itself. So every point group has the identity element. There's that principal rotation along the axis that contains the principal rotation axis. We're going to call this z-axis in our derivations. And this is 180 degrees, right? Because it's a 360 divided by 2, 180 degrees. And so if you imagine spinning this axis along this axis 180 degrees, we're going to take this hydrogen, spin to that hydrogen, this hydrogen, spin to that hydrogen, and all 3 carbons are going to remain unchanged. And then lastly, we have this, what we call, not lastly, but next, we have this S4, which S, remember, stands for improper rotation axis. And so this is actually technically our principal rotation axis. It's improper because it only exists followed by a mirror plane, but it has a higher n than the C2, although it's still coincident with the z-axis, what we're defining as the z-axis, our principal rotation axis. You can see what happens here is this hydrogen's moved in front, and then it's flipped down through the mirror plane to go there, and this hydrogen is moved, moved 90 degrees, right? We do a C4. Remember, an S4 is defined as a C4 followed by a sigma H, a horizontal mirror plane perpendicular to that C4. So again, just like here, we did a 90 degrees, and then we flipped. Here we do a 90 degrees, and then we flip back down to that back hydrogen. And then we also have the perpendicular C2s. And just like we said, up here, we're going to have n perpendicular C2s. Well, n is 2, this value right here in our point group name. So we're going to have 2 perpendicular C2s, and here they are. And these are quite difficult to visualize. Among the harder operations, I think, throughout symmetry space to visualize. But basically, what ends up happening is these 2 hydrogens bend down in both cases to these 2 hydrogens, and they just are twisting different ways to get there. And so, you can go on the Symmetry at Otterbein website and visualize these. That's where I took these screenshots from. And finally, we're going to have our 2 sigma d. So anyway, here we'll call these, here we have actually 2 that we did at once, right? So we could call these C2 prime and C2 double prime. And here we have our 2 sigma d's. These are dihedral mirror planes, and their d's or v's are always coincident with the principal rotation axis, so they contain the z-axis. The z-axis goes through them, unlike the horizontal mirror plane, which is perpendicular to it. There isn't a horizontal mirror plane in this molecule, but we invoke it when we're doing the improper rotation axis, right? Because if we just do a flip, sigma h, this atom goes to that atom, so there's no horizontal mirror plane. But there are these dihedrals, and whether you call these sigma v's or sigma d's, doesn't really matter too much, but we know there's no DNV point groups. There's no D2v point groups. And so because, the name here is D, we're going to call them sigma Ds. And you can see this one right here cuts through and takes this hydrogen to that hydrogen and goes through, contains these hydrogen. And then the other mirror plane does the opposite and flips these two hydrogens. So we can call those sigma D and sigma D prime. I didn't make it clear earlier. I didn't. I'm using hat notation here. Hat notation denotes an operation. And now what I'm going to do is use class notation when we group these symmetry operations into classes. We've come up with all of the symmetry operations that there are for this point group. And there are 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. And so from here, we just carry on. And from here, we carry on and group these into classes. Now, we did have one more symmetry operation that we need to check here. We have to also check derivatives of all these things. So that's a good thing to do. Identity, if you do it, like what I mean by that is what happens if you do the operations multiple times. Identity, if you do identity twice, you're just going to get identity, just multiplying by 1 twice. C2, if you do, we could write C2 twice, that's going to be equal to identity. So that's not a unique operation. Doing mirror planes twice will get you back to identity. Doing C2s the other way, the perpendicular C2s twice will get you back to identity. What about the S4? That's an interesting one, right? So S4 twice is equal to C4 twice, and then also doing a sigma H twice. Sigma H twice, we flip once and then flip back. So you flip bottom to top, let's say, and top to bottom. That's just an identity. So this equals actually C4 twice, and a C4 twice is just a C2, which is what we had here. So S4 twice is not a unique operation. S4 3 times is equal to C4 3 times, followed by sigma H 3 times. And if we have 3 mirror planes, that is the same thing as doing 1 mirror plane. So you can think about going bottom to top, 1, top to bottom, 2, bottom to top, 3. That's the same as just doing 1 mirror plane, bottom to top. So you end up with this, and that's not anywhere else, okay? And so we can kind of think about that as when we're drawing this before, we had rotating 90 degrees one way. Now we're doing a 270 degrees. So this hydrogen actually gets flipped there, and then we do the sigma H. An alternative way of kind of defining that is if you define the axis systems different ways, and rotate the other way, just do an S4, you do the same thing. So S4 and S4-3 are very similar. One is just counterclockwise, one's the clockwise, right? And because actually there's equivalent axis systems that will make these equivalent, and you can interconvert between these 2 different axis systems using a sigma D, which ends up being the case. That's a symmetry operation that allows you to interconvert. What that tells you is that these S4-3 and S4 operations have to be in the same class. So we group them together. And this sort of makes intuitive sense. So that consists of the S4 and the S4 3 times. It makes intuitive sense. They're both in proper rotation axes. And so we put them together, but mathematically rigorous because of the reasons I just stated. So similarly, we're going to put the 2 dihedrals And by the way, an S4 four times just gets us back to identity because that's a C4 four times and a sigma H four times, and sigma H four times is identity, and C4 four times, right? 360 degrees, 90 times 4 is also identity. So we have our two sigma Ds. We're going to put those in the same class. You can see that the sigma D and sigma D prime do very similar things. They both just flip one of the hydrogens. The perpendicular C2s, those are going to go in the same class. And then we just have this other C2, which we can call C2Z or just C2. If we want, we can put a Z just to make sure we know that this is going across the principal rotation axis. And then we have identity. So actually we have 8 operations, and we're going to group them into 1, 2, 3, 4, 5 classes. So now we can go to a blank page here, and we can draw out the sort of skeleton of our character table. We always put on the top left D2d, the point group of the character table deriving. And we start off by convention just with the identity operation. And I'm dropping the hat notation because we are talking about classes. A lot of character tables, what they'll do is they'll put the principal rotation axis class first. This is actually going to be the S4, it's the highest order N. A little unconventional there. A lot of times, almost all the times, there's only very few examples, these D&D character tables where you have an even N, this ends up happening, where your principal rotation axis is going to be improper. Most of the time it's going to be a CN, right? Not an SN or SN, S2N technically. But anyway, then we have that C2Z by itself, how we talked about, also going along the principal rotation axis, that 180-degree rotation. We have the 2 perpendicular C2s, so called the 2C2 class. And lastly, we have the 2 sigma D mirror planes. So that gave us a total of 1 plus 2 plus 1 plus 2 plus 2 is 8. Okay. And so we at this point have 5 classes. So we're by our character table rules video, and please see the character table rules video that I made. Our first character table rule is that the number of classes has to equal the number of irreducible representations, or as I like to call them, just vectors, because that's what they are. We're doing linear algebra here. We're doing abstract linear algebra or multiple dimensions. We are in 5-dimensional space, right? Because we have 5 components to each vector. We're in 5-dimensional symmetry space. And so eventually we're going to give these Mulliken symbols. That's going to be the very last step in deriving the character table. Just a series of rules that we use to help chemists easily identify the certain key aspects of the vectors without having to look at the character table necessarily. So when we're talking about them, it's easy to kind of, talk about it without having to be staring at a character table. And also, so we have a uniform set of rules to communicate with one another about them. But we're going to do that at the end. We need to know what the vectors are first before we can assign the Mulliken symbol labels. But the first irreducible representation is always going to be 1s across the board, right? Totally symmetric rotation, irreducible representation. And then we don't know what these values here are under the dimensionality or under the identity of the character. But we know another character table rule, again, see the character table rule video, is that the sum of the squares of the dimensionality has to equal the number of operations in the point group, which is also called the order of the point group. So in this case, what that means is 1 squared plus a squared plus b squared plus c squared plus d squared has to equal 1 plus 2 plus 1 plus 2 plus 2, which, we figured out before was equal to 8, the total number of symmetry operations in the point group. And these values, these dimensionalities, have to be equal to 1, 2, 3, 4, 5. And most of the time, you're just going to have 1s and 2s. 3, 4, and 5 only come up in very highly symmetric point groups. And so the only way to for this equation to be valid, if you just look at this for a little bit, is to have all the numbers be ones except for one of them. So we'll arbitrarily just call the gamma 5, give that a 2. But 1 squared plus 1 squared plus 1 squared plus 1 squared plus 2 squared is equal to 8. All right, at this point, it's easiest to start deriving the other irreducible representations using functions. I always like to start off with the z function. So what I mean by that is we're going to draw our axes here, and we have to remind ourselves that our principal rotation axis is always along the z-axis, right? So we're going to be doing our S4 here, and also our C2z, right? So these two classes, operations from those two classes. And when we talk about a z-vector, we're imagining a vector pointing along the z-axis. And so what we're going to do to that z function is apply each of the symmetry operations to it. So we ask ourselves, what happens to the z vector when we apply an identity operation to it? Well, z goes to z. And then we think about what matrix describes mathematically this transformation. Well, it's a 1-by-1 matrix where z multiplied by a 1-by-1 matrix, including that it contains the element 1, is equal to z. And then we take the trace of this matrix, or the character of the matrix, which is where the name character table comes from. The character of a matrix is the sum across its main diagonal. Here we only have a 1-by-1 matrix, so we just take the element 1, and we're going to write chi, which just means character of the identity operation equals 1. That's what we figured out from this. And so we already had that down here for 4 of our irreducible representations using our other rule, but that's how we'd start. Now we're going to go in a very similar manner with the S4. Now the S4, remember, is going to rotate 90 degrees along this z, wrapping around the z-axis. So you have a vector pointing up, and you're rotating that 90 degrees. Well, if you're rotating it like this, right, wrapping around that axis, it's still pointing up. So when you do the C4 part, remember an S4 is a C4 followed by a perpendicular mirror plane, a sigma h. Remember from earlier that sigma h is perpendicular, stands for horizontal, so it looks like that. It's in the xy plane. So that C4 part of the S4 operation does nothing. It's 90 degrees, and the vector's still pointing up. But then, when we do the sigma h part, it's going to reflect down. The vector is looking at itself in the mirror plane, and so net z is going to negative z, and so the matrix that describes this transformation is z times -1, which equals negative z. Take the trace of this matrix, the sum across the diagonals, and get that the character of the S4 operation equals 1. If you're curious, equals -1, right? The sum across the diagonals, which is this element. So now we've derived a new function, and I put it under here, thinking that, guessing that it, without doing any computations, that in my head, that it would transform as gamma 1, but it obviously doesn't. It transforms as something new. So we'll put the z down here because we have this -1 here, making it unique from all the ones across the board. You might be wondering what would happen if instead I chose the S43 operation, right? That's another operation in this class. And that's, of course, C43 followed by 3 sigma h's, which is the same as sigma h. So we've gone over it before. Well, that's a 270-degree rotation at first. That still does nothing to the z vector. And then you do the flip, and z goes to negative z, and you get -1 again. So this is the beauty of the character table. Anything in the same class will give the same character. And so it's another way of thinking about what it means to be in the same class. Okay? And the character really kind of embodies that key quantitative information about what this transformation does in this symmetry space, what this operation does, or this class of operations, what this class of operations, each of those operations do. All right, So what about C2z, call it? Well, that's 180-degree rotation. But the vector is still going to be pointing upwards. So z goes to z. And again, we get this situation where the character is going to be equal to 1, just like we did for identity because z went to z. So if z goes to z, you're going to get 1. Z goes to negative z, you're going to get negative 1. C2. Well, there's two C2s. They're both perpendicular. I could define one as along the x-axis. Why don't we do that? So erase this here. And now we're thinking about a perpendicular C2, called C2 prime. And it's flipping 180 degrees. So again, now we're flipping it along perpendicular things. So it's going to spin the vector downwards. And so z is going to go to negative z. So again, that gets us a character this time of, sorry, for writing, negative 1. Last one for the z function are sigma d's. Which sigma d do we choose? It doesn't matter, okay? And we can think about how these sigma d's are oriented with respect to the C2s. And they turn out to be why they're called sigma d's is they bisect the C2s. So they go 45 degrees. So it ends up for this calculation for the z-axis not mattering. But to be rigorous here, if we're to draw one of our mirror planes, or two of them, remember, it doesn't matter what symmetry operation in the class we choose, we just need to choose one of them. We'll get the same character. That's why they're in the same class in the first place. So we're going to draw this at a 45-degree angle like that. And you can see that this mirror plane contains the z-axis, and anytime a vector or a point or whatever is inside that mirror plane, the mirror plane does nothing. And so you get z going to z. And so you get your character equaling to 1. And so we have completed our gamma 2. A good thing to check is that this representation is orthogonal to our only other vectors. And what that means is the dot product has to be equal to 0. We only have one other vector, which is gamma 1. But when we have gamma 3, gamma 4, and gamma 5, all those combinations will be, dot product will be equal to 0 as well. And this dot product, so let's write out gamma 1. I'm going to add some space here. And I'll show you why in a little bit. But we have the vector 1, 1, 1, 1. And we're dotting it with gamma 2, which is 1, negative 1, 1, negative 1, 1. And the rule is here, you have to adjust for the number of symmetry operations in each class. So what I mean by that is we have to multiply one of the vectors by the number of symmetry operations in each class. Well, in identity class, we only have identity. We only have 1. In the 2S4 class, well, the 2 tells us we have 2, so we have to multiply by 2. C2 only has 1. 2C2 has 2. And 2 sigma d has 2. And so now this simplifies to just 1, 2, 1, 2, 1, dotted by gamma 2, which stays the same. And this equals, right, the dot product is we multiply each component of each vector, 1 times 1, and then add them. 2 times negative 1 plus 1 times 1 plus 2 times negative 1 plus 1 times 1. we made a mistake here. This was a 2, and I did write a 2, but I couldn't even read my own writing. It's not good. And so this was supposed to be 2. And so this is supposed to be 2 times 1. It happens, you make mistakes. 1 plus -2 is -1, plus 1 is 0, plus -2 is -2, plus 2 is 0. So they're orthogonal. So that's good. It's a good check. We didn't get orthogonality there. We did some logic here. There's some visualization process wrong there. A lot of this is visualizing, right? All right. Next one I always like to do is x. And I know where it ends up transforming a priori, so I put it down below. You don't know that. Okay, so I'm gonna erase here. And what we're gonna do is we are going to ask the questions just as before, what we did. And so we go through all the different symmetry operations, and our first operation is going to be identity, of course. And an identity, of course, x is going to go to x. So that's not very interesting. But what's going to happen when we do an S4? That one's a lot more interesting, right? Because our S4, 2 S4s are next class. So let's just write this out. Okay, back in action. X goes to X. C, S4. We can do the S4 or S4-3. Let's just do S4 for simplicity. Remember, that's a C4 followed by sigma H. So what's going to happen when we do a C4? Well, and let's draw our X vector here along the X-axis. Well, we're going to do C4Z. That's going to take X into Y. And then we are going to, because it's a 90-degree rotation, and then we're going to flip across the horizontal mirror plane, but the horizontal mirror plane is in the XY plane. So Y vector is in that plane, so that does nothing. So X ended up going to Y. Well, that's kind of interesting because so X goes into Y. And so what that tells you is that you cannot describe how the X vector transforms by the S4 operation without also invoking Y. Another way of saying that is that X and Y transform together. And so X is defined in terms of Y, and Y actually has to be defined in terms of X. And so if you think about the Y vector now, I'll use a different color. For the Y vector is going to spin 90 degrees into negative X. And so now we actually have a 2x2 matrix that describes this transformation. And it looks like this, using our row column matrix multiplication rules. 0, 1, and -1, 0. And that gets you from xy to y at -x. Now you can see why earlier I stressed taking this trace of the matrix. It's going to be the sum across the diagonals. The character of this transformation is 0 plus 0, which is equal to 0. So under S4, we can put 0. And there's going to be a 2 here because there's 2 functions that go together. And so back on identity, we have to now pair it with y. And so we're going to get the identity matrix with 1s across the diagonal. And we get that the character for identity is 1 plus 1, which equals 2. And that's why we have a 2 here. All right, keep moving on. C2. C2 is a 180-degree rotation. No mirror plane. It's a pure rotation. So what's going to happen there? Well, there's our x vector. It's going to spin 180 degrees behind itself. The y vector would do a very similar thing where it spins 180 degrees behind itself. So mathematically, x went to negative x, y went to negative y. We have to maintain them together, and by a 2x2 matrix, now we have the inversion matrix, negative ones on the diagonal, and that equals that. Character, and 4 is a sum across the diagonal, -1 plus -1 equals -2. All right, we're on to the C2s that are perpendicular. Call them C2 prime. We defined it last time. We have to be consistent with our definition when we did the z function, right? We defined it as being along, we chose a mirror plane that was along the x-axis. And so if we're rotating along the x-axis, just like earlier when we were doing the z, we're rotating along the z-axis and nothing happens. Nothing's going to happen here. It's just going to continue pointing forward. Doesn't matter how much we rotate it by along the z. So that means x goes to x. And what about y? Well, y gets flipped. Right? Boink. It's pointing this way, and then it got rotated like that, going that way. So y went to negative y. One, -1, 0, 0. Well, x and -1. I of C2 prime is equal to 0. Last one, sigma d's. For sigma d's, sigma d, one of the sigma d's, the sigma d that we used before was bisecting at a 45-degree angle the x and y axes. And so if we think about an x vector, it's now looking at itself 45 degrees away from the mirror plane. So it's going to end up reflecting 45 degrees on the other side of the mirror plane. That makes it 90 degrees from one another. So x is going to go to y. And well, if you're a y vector and you're looking at yourself from the other side, you're going to turn to x. So y goes to x. So x goes to y goes to x. The matrix that describes that is 0s on the main diagonal and 1 on the off diagonal. Take the trace of that matrix and you get 0. Character sigma d is equal to 0 plus 0, which equals 0. So there we have it. We derived the gamma 5. Okay, so it's always good to check orthogonality, so we can do that. Easiest one to check orthogonality with is gamma 1. It's totally symmetric, so I like to start there because very quickly I can see if I made a mistake, if I'm wrong. And the reason why that one's so easy is because it's all ones across the board, so we just have to multiply by the number of symmetry operations there. Remember, we have to test orthogonality adjusting for the number of symmetry operations in each class. And so we have 2 times 1 times 1 is 2 plus 0. Oh, well, that does nothing. Plus -2 times 1, that's 0. And then these other zeros, we've been adding those up, and those do zeros. So we're orthogonal with gamma 1. We could do the same thing with gamma 2, and it's nice when you have a character that has some zeros in it, so you don't even have to think about those ones. So here it's just identity, 2 times 1 times 1 is 2 plus -2 times 1 times 1, again, 0. So we're good. Gamma 5 is orthogonal with our two other functions. All right. So now we can carry on to figuring out gamma 3 or gamma 4. It's arbitrary where you call, what you call each one. And so let's test some other functions. We've done all the linear functions, x, y, and z. So let's start doing quadratics. And so a nice place to start is to think about multiplying functions together that we already have. And we can make quadratics like x times z and y times z. Okay, those are going to transform together. It's already telling us that. And what is our function going to be? Well, it's going to be 2 times 1 is 2, 0 times -1 is 0, -2 times times 1 is -2, 0 times -1 is 0, and 0 times 1 is 0. So unfortunately, that just gets us back gamma 5. But we figured out that xz and yz transform thusly as gamma 5. Didn't help us, so let's do something else. You could think about z squared. 1 squared, -1 squared, 1 squared, -1 squared, 1 squared. Those are all ones. That's going to transform. It's totally symmetric. Didn't help us. What are other d functions? xy, right? Let's do xy. And then the last d orbital function is x squared minus y squared. So xy. Well, xy, doing identity to that, is xy. S4. How do you figure out what xy does? Well, if you remember, the S4, S4 is a C4 followed by a sigma h, but sigma h is in the xy plane, so sigma h doesn't do anything. So really we're doing a C4, x went to y, and y goes to -x, that last time. So we're gonna end up with x going to -xy, right? -x times y. So maybe we're getting something new here. I'm not going to show all the matrix work, but we know if we go to itself, we get a 1. And here, if we go to negative self, we get a -1. C2. C2, x went to x, y went, sorry, C2, x spun around to -x, y spun around to -y. And so that ends up being xy going to -x times -y, which equals to xy. So that's a 1. C2 prime. So we can add a 1 here. C2 prime. Well, if we define it as a C2, x is going to stay as x, and y is going to go to -y. So xy goes to -y times x, which is -xy. That's going to be a -1. Sigma d. Sigma d, x goes to y went to x, so xy goes to yx, which is equal to xy, we get a 1. And look what happened, we got the same function back as gamma 2, so we better put xy up there and erase our work. We did not generate anything new. Let's keep trying. What about x squared minus y squared? X squared minus y squared. Well, we have some nice math here, of course, for identity. It's going to go to itself. Here we have x going to y. So x squared minus y squared goes to y squared minus x squared, which is equal to y squared minus x squared, which is equal to negative of x squared minus y squared, so we get a -1. What about for C2? Both go to the negatives of themselves. So x squared minus y squared goes to quantity -x squared minus quantity -y squared, which just equals x squared minus y squared, which is what we got. So 1. And then if we do C2, well, x went to x, and y went to negative y. Well, you're going to square that negative y, and it ends up just going to therefore x squared minus y squared. So we generate something new that's going to get us a 1. And sigma d, x squared minus y squared, x went to y, and y went to x, you get y squared minus x squared, which equals negative what you started with. So lo and behold, you get a negative 1. That is something new, folks. It turns out everything's orthogonal. You can check that if you like, but it's quite nice. Okay? In this case, we've run out of quadratic functions, and there's a couple of things you can do. You can stare at this for a while and figure out, using the orthogonality rules, what this last one will be. Okay? And I think in this case, that's quite easy. It ends up being this way. And basically, the reason why I was able to do that so quickly is, well, we figured out a lot of the other ones. But if you notice, we always have two negative ones for these ones that have negative ones. And the negative ones fall underneath the twos. And the reason why that has to be is because if you are to be orthogonal with gamma 1, you only have 5 classes. And so you need 2 of your 2's to be negative ones. So you get a negative 4. And then you need your other 2 and your 1 and your 1 class, for example, to be positive 4. 2 plus 1 plus 4. So that's how I was able to figure that out. And you could check all these orthogonalities and it'll work. There's another way you could do it. There's a cubic function that works here. It's z times x squared minus y squared. And so in that case, that's just taking the z function and multiplying by this function. Weirdly, there's also a quartic polynomial, xy times x squared minus y squared, that would have this, right? Because we know both z and xy transform as a symmetry, but that's not really a very useful function. Cubic functions are used in f orbitals, right? So there we have it. We've derived the character table. Again, that last trick there is just, multiplying gamma 2 by gamma 3. We got this new function here. All we have to do is come up with the Mulliken symbols now, the most rewarding part because you've done all the hard work. And you just have to follow these simple rules. Give it a value of e if you're a dimensionality of 2. That means the character underneath identity. These e's are different. This is the Mulliken symbol e referring to this 2, 0, negative 2, 0, 0 vector. This is the identity class, right? And then if you're a 1, you give it an a or a b. How do you decide which one? If you're symmetric with the principal rotation axis, you give it an a. The principal rotation axis, remember, as we discussed, is weird in this case. It's actually an S4. It's an improper rotation axis because you have the highest value here. So the ones with positive values, with 1s here, you give A's. The ones with negative values here that are anti-symmetric, you give B's. And then the rule is to look at perpendicular C2s. If you don't have any perpendicular C2s in your point group, you look at sigma V's. We don't have any sigma V's, and we do have a perpendicular C2s, so we just look at that. For symmetric with respect to that, meaning we have a positive number, in this case a 1, we give it a subscript 1. So this is symmetric. It would be A1 Mulliken symbol. We're done naming it. This is symmetric. It would be the B1 symbol. If you're antisymmetric, you give it a 2. Negative 1s. And that's it. Here's what you might look up online. You can see we have various cubic functions with z squared. We didn't do this x squared plus y squared. It doesn't transform as a d orbital, but you can see we got all this right. We didn't talk about the rotation vectors, but we've done that in other videos. We could have done that instead of using the cubic function. Would have been a third way to derive that one. Remember, we showed orthogonality or this cubic function. And we got the Mulliken symbols right and the 5 classes in all the character tables.